Hello, my name is Dr. Roderick L. Roll, and today I will be talking to you about the properties of acids, bases, and buffers. Acids are solutions that release excess hydrogen. These solutions are hydrogen donors. One example of an acid is hydrochloric acid. Hydrochloric acid is HCl. When the H and the Cl dissociate or separates, the hydrogen drives down the pH. Bases release OH groups or hydroxyl groups. The OH is going to tie up the excess hydrogen. When an OH binds with an hydrogen, it makes water. A classical example of a base is sodium hydroxide. Sodium hydroxide will dissociate into sodium and OH hydroxide ions. Some acidic solutions are carbonated beverages. Some alkaline foods are things such as vegetables. Acidic solutions have a lower pH, pH below 7. Alkaline solutions have a higher pH, pH above 7. Acidic solutions range between 0 and 6.99. Basic solutions range from 7.01 to 14. A neutral solution is pH of 7. An example of a solution is blood. Blood has a pH of 7.35 to 7.45. Use this image to the right to look at some common foods to see what their pHs are. We'll first talk about acids. I'm going to discuss two types of acids: strong acids and weak acids. Hydrochloric acid and sulfuric acid are examples of strong acids. These solutions will dissociate or dissociate completely. So for example, if we have 100 units of hydrochloric acid, it will separate completely. It will produce 100 hydrogen ions and 100 chloride ions. So therefore it is called a strong acid. Hydrochloric acid is the acid that is located in your stomach. Sulfuric acid is the acid that is located in a battery. So let's talk about hydrochloric acid and the benefits of it. If you look at the first image to the left, we have 3 test tubes. The first test tube is just hydrochloric acid with a protein, a piece of meat. As you can see, the meat is just floating in the hydrochloric acid. The second test tube is pepsin in a solution with meat, a protein. Pepsin is the enzyme that's in your stomach that digests proteins. The third test tube has pepsin, the enzyme that breaks down meat, hydrochloric acid, and meat. As you can see in test tube 3, the meat is gone. So in order for the enzyme pepsin to work effectively, the pH of the stomach has to be 2. It has to be acidic. Therefore, hydrochloric acid has to be produced. If you could somehow alter the pH of the stomach to be above pH 2, then the hydrochloric acid would dissipate, and pepsin would no longer be functional. Then you would therefore have digestive issues. Let's look at weak acids. An example of a weak acid is carbonic acid and acetic acid. Acetic acid is the acid that is used to make vinegar. Why they call it a weak acid is because it does not dissociate completely. So if we have 100 units of a weak acid like carbonic acid, 90 molecules will stay as carbonic acid, and 10 molecules will separate, or 10 units would separate. Therefore, if you were trying to alter the pH of a solution, and the solution's pH was 7, and I told you I need you to lower the pH from 7 to 6.8. Would you use a strong acid or a weak acid? The answer is you would use a weak acid. If you used a strong acid, the pH would go from 7 to maybe pH of 3. You would overshoot the pH range that you were trying to achieve. So, weak acids versus strong acids. The strong acid will separate completely, therefore releasing a large amount of hydrogen ions, whereas the weak acid will only release a few hydrogen ions. The next slide we'll look at talks about concentrations of hydrogen ions also. We have hydrochloric acid, and we have 1 mole concentration versus 0.1 mole concentration. Now let's talk further about moles. So in the previous slide, we looked at 2 different concentrations of hydrochloric acid. So a mole of an element or compound is equal to its atomic weight or molecular weight in grams. This will help with proper comparison during experimentation. So in reference to moles, it's sort of like looking at percent. If you want to compare an apple to an apple, you need to compare 1 apple to 1 apple. Or if you want to compare 1 apple to 1 orange, you cannot compare 1 apple to 10 oranges. So using percentage or using moles will help you standardize your experimentation. So further in this slide, I show you the molecular weight of glucose, caffeine, and THC. THC is the component in marijuana. So if we were going to do an experiment to see which of these 3 drugs is more effective, you have to compare 1 apple to 1 orange to 1 grapefruit. So you can't compare 1 apple to 10 oranges. So that's why we use molar concentration or percentage. So I'm going to show you how to calculate moles. So the first thing you needed was the molecular weight. So the molecular weight of glucose is, with the way to calculate the molecular weight is you have to know the formula, which is C6H12O6. Then you have to find the atomic weight or atomic mass of carbon, atomic mass of hydrogen, and the atomic mass of oxygen. Atomic mass of carbon is 12.01 times 6 carbon. Hydrogen is 1.008 times 12 of them, and oxygen is 15.99 times 6 of them. This will help you figure out the molecular weight of this molecule of glucose. So in order to make 1 mole solution of glucose, I would have to use 180.156 grams. Where did I get this number from? I got this number from the molecular weight of glucose. So I would measure out 180.156 grams of glucose into a container, and then I would add 819.844 milliliters of water. This would be in a 1 liter container. When I mix this up, I would have 1 mole solution of glucose. If I was comparing this to caffeine, I would have to take the molecular weight of caffeine and do the same process. Let's say it ended up being 500 grams. You would take 500 grams and mix it with 500 milliliters of water, and that would give you 1 mole of caffeine. Then you could compare caffeine to glucose. If you do not compare 1 mole of caffeine to 1 mole of glucose, it's not an accurate experimentation. So with this slide, I would like for you to figure out how to make a 3 mole solution of glucose. So a 3 mole solution of glucose is a higher concentration of glucose. So therefore, that's 180 number that I gave you previously. You times that by 3. The number would be 540.468 grams of glucose mixed into a container with water. And the total volume, once you put the water in, would be 1 liter. So 1 mole of any substance is always the same number of molecules, and that number of molecules is 6.02 times 10 to the 23rd. This is known as Avogadro's number. So again, if we are measuring, if we're doing an experiment and comparing glucose against water against methane, you want to compare 1 to 1 to 1. That is why we use mole. So 1 mole of each contains 6.02 times 10 to the 23rd molecules. So how to compare drugs? If you were to compare alcohol to heroin, to cocaine, to tobacco, you have to use moles, or the experimentation would be faulty. So 1 mole of glucose versus 1 mole of THC, I would take 180 grams of glucose and mix it into water and bring the volume up to 1 liter. And then I would make another container with THC, and I would have to add 314 grams of THC and bring the volume up to 1 liter. If I have those 2 containers, then I can inject those into a vein, and then we can compare some kind of physical response. So that would be comparing 1 mole to 1 mole, which is 6.02 times 10 to the 23rd molecules of glucose versus THC. So this slide shows again hydrochloric acid. We have 1 mole concentration versus 0.1 mole concentration. So this should make more sense to you now. The one on the left is 10 times less than the one on the right. So the one on the right has 10 times more hydrogen ions than the one on the left. So now let's talk about bases. A classical base is sodium hydroxide. This is a strong base. It easily dissociates, it easily separates, and the OH ties up the excess hydrogen that is in the solution. Another example of a base is sodium bicarbonate. Sodium bicarbonate is better known as baking soda. This is a weak base. It will not totally separate or dissociate, but when it does separate, the bicarbonate would tie up excess hydrogen. When the bicarbonate binds to hydrogen, it becomes carbonic acid. Carbonic acid is going to be very important when we talk about buffers. So what are buffers? Buffers are solutions that resist abrupt and large swings in the pH of body fluids. The buffer that we will talk about is the buffer that is in the blood. Remember that the blood's pH has to be within this narrow range of 7.35 and 7.45. So this is known as the carbonic acid bicarbonate system. You have to remember this formula. The chemical equation between carbonic acid and bicarbonate resists physical change in the blood. How? It resists the change by dissociating or reforming. So we're going to go over several examples to show you how this works. This slide shows the narrow range that the pH of blood is supposed to be. If the pH is below 7.35, you have what is called acidosis. If it is above 7.45, you have what is called alkalosis. But quickly, the carbonic acid bicarbonate buffer system will shift the pH back to where it is supposed to be. If it does not, then you might have a serious respiratory acidosis issue, or metabolic acidosis, or respiratory alkalosis, or metabolic alkalosis. So we have a series of questions that we need to address now. So question 1 is asking, if the pH is high, around pH 10, how could we lower the pH using the blood buffer system? What molecule must react and how? So take a few minutes to address this question. What you're looking for is, you're trying to decide if carbonic acid is going to step up and do its job, or is bicarbonate going to step up and do its job. If carbonic acid does its job, it will dissociate, therefore releasing hydrogen. If bicarbonate does its job, it will accept hydrogen from the solution. The answer is carbonic acid is going to step up. It is going to release hydrogen into the solution, and it's going to therefore change the pH. It's going to drive the pH from 10 down towards 7, down towards 3. So carbonic acid will dissociate. This is a weak acid. So just as I described previously, the excess hydrogen will drive down the pH. Question number 2. If the pH is low, around 2, how could we raise the pH using the blood buffer system? So which of those two players are going to be involved? Is it carbonic acid or is it bicarbonate? We're trying to change the pH from 2 to maybe 5. The answer is bicarbonate steps up. So bicarbonate is going to combine with the excess hydrogen. If it pulls excess hydrogen out of the solution, it's going to change the pH from 2 to 5. Question number 3. I want to increase the blood acidity from pH of 5 to pH of 2. I'm therefore trying to drive down the pH. I'm trying to therefore increase the acidity. How can this be done using the blood buffer system? I'm trying to change it from 5 to 2. Who is going to step up, carbonic acid or bicarbonate? The answer is carbonic acid is going to dissociate. It is a weak acid, and it will separate when you put it into solution. It's going to separate, releasing hydrogen, and the hydrogen is going to drive down the pH or increase the acidity. Question 4. I want to decrease the blood's acidity. So I want to take the blood from 7.3 to 9. So I want to decrease the acidity, therefore increase the alkalinity. How can this be done? Which of the players need to step up? Carbonic acid or bicarbonate? Lowering acidity really means to increase the alkalinity. So the answer is we have to change the pH from 2 to 5 or 7 to 9. Bicarbonate accepts more hydrogen. When it pulls the hydrogen from the solution, bicarbonate turns into carbonic acid. This will therefore drive the alkalinity up. So now we're done with those problems. Now we're going to look at how to calculate pH. And what is pH? So the pH scale is a mathematical way to look at concentrations of hydrogen ions in a solution. So all solutions have hydrogen ions. We can calculate and we can give a number to the solution based on its acidity or its alkalinity. So in a solution, the product of hydrogen ions and hydroxide ion concentration is constant, and this number is 10 to the negative 14. So below we have an equation that you need to remember. It's the molar concentration of hydrogen ions times the molar concentration of hydroxide ions, and this equals 10 to the negative 14. You have to input that into your memory. So a neutral solution at room temperature has 10 to the negative 7th hydrogen ions and 10 to the negative 7th hydroxide ion concentration. So 10 to the negative 7 is 1 in 10 millionth. The more acidic the solution, the more hydrogen ions it will have. The more basic a solution is, the less hydrogen ion it has. So everything is based on the hydrogen concentration. So the brackets that we've been seeing indicates molar concentration, and we just went over molar concentration. It helps to standardize solutions. So by employing a logarithm, this pH scale is more conveniently expressed from 0 to 14. So I'm going to show you how to calculate the pH. So first you need to know this formula. pH equals negative log of the molar concentration of hydrogen. So all you need to know is this solution has how many hydrogen ions. If you know how many hydrogen ions are in the solution, you can calculate the pH. So an example is we have 10 to the negative 7 concentration of hydrogen, or 1 in 10 millionth of hydrogen ions. So you just put this in that simple formula and you get negative times negative 7, which equals 7. So that the pH is 7. So I have a few questions I would like for you to address now that you have that formula imprinted into your memory. If I gave you the hydroxide ion concentration, what is the hydrogen ion concentration? You have to use the formula to figure this out. So the first thing you need to do is set up the formula. The formula is the molar concentration of hydrogen ions times the molar concentration of hydroxide ions equals 10 to the negative 14. So if I give you the molar concentration of the hydroxide ions, which was 10 to the negative 12, you put that into this molar concentration, and you just have to figure out what is the molar concentration of the hydrogen. And the answer is 10 to the negative 2. This is just another way to look at it if I gave you this scale, which I probably will not. So just make sure you understand how to use it the mathematical way using the formula. So in red to the bottom, it has it set up. The molar concentration of hydrogen is 10 to the negative 2. That is times the molar concentration of the hydroxide ion, which is 10 to the negative 12. And remember, that has to equal 10 to the negative 14, which it does. 12 plus 2 is 14. So what was the pH? Remember, to figure out the pH, you have to know the hydrogen ion concentration. So the first number, 10 to the negative 2, is in reference to hydrogen. So whatever that number is, that's your pH. So the pH for this example is 2. Now, if I gave you the hydrogen ion concentration and asked you to tell me what is the pH, could you do it? So the answer to that second question was pH 12. I gave the example and I wrote exactly how to figure this out. So make sure you're able to calculate pH. So now if I give you 4 examples, and here's the question: what is the hydrogen ion concentration for the following solutions? So I'm asking, what is the hydrogen ion concentration? You could say 10 to the negative whatever, or you can give me the actual real value, 1 in 100,000, or 1 in 1 million, or 1 in 10 million, or 1 in 100 million. This would be the answers to the question I just asked. Now, with those same pHs, what is the hydroxide ion concentration for the following solutions? This would be the answers for the hydroxide ion concentration.